Okay, so discussion 2. Now we're looking at problem 17 from the book, where we have a small object, 3.8 grams, and with a charge of negative 18 microcoulombs, suspended motionless above the ground when immersed in a uniform electric field perpendicular to the ground. What is the magnitude and the direction of the electric field? So we have an electric field, and then we have an object that's just hanging out above the ground because it has a charge on it. Right, this object has a charge, and the electric field is interacting with that charge. So we want to figure out the magnitude and the direction of the electric field. Where do we start? Okay. Let's just, I like to rewrite. Well, it's fine. What do we have? 3.8. Okay. So we have two forces happening. We have the interaction of the E field, and we have the gravitational weight force, and they're in equilibrium. Right? In equilibrium. So we set up the sum of our forces, which means that now we have Fe is equal to Fg, which is our weight force. And now, since we're talking about an interaction of a charge with an electric field, the force is just Q times E. That's equal to mg. So E is going to be equal to mg over Q. And we just plug all that in. We plug in our mass, 3.8 grams, 3.8 times 10 to the negative 3 kilograms. Got to be careful of your powers of 10 and your units. Times 9.8 meters per second squared. 1 over, what was it? It was 18 microcoulombs. Negative 18 times 10 to the negative 6 coulombs squared. Right? Nope, sorry, that's not squared. Okay, and that gives us a value of approximately 2.07 times 10 to the 3 newtons per coulomb for our electric field, which is what I got. And the force is going to be, we're asked to find the, sorry, I'm just double checking my work here. Direction of the electric field is going to be pushing upwards. I mean, there's no other way. Oh, it's a negative charge, so it's actually going to be pushing downwards. It's actually pushing downwards. Right, because the negative charge would actually be going that way. So, magnitude, direction, down. Okay, next, number 21. Looking at the book here, we have 3 charges. Nope, we have 2 charges, and then we want to find at what point does the electric field go to 0. So we have charge 1, Q1. And then we have Q2, charge 2. Excuse me. This is at x equals 0. This is at x equals 2 meters. We want to find what point does this go to 0 along this line. So this one is 3 nanocoulombs, and this one is 1 nanocoulomb. So my estimation would be that it's going to go to 0 around here, just based on the size of it. This one's much larger, so it's going to have a longer distance. Okay, so to set this up, we essentially want to have, so the sum, so we're looking for kq1 over the first distance squared plus kq2 over the second distance squared, right? We'll call this R2, this is R1, right? This is going to be equal to 0. That's what we're looking for. But it's not just this distance, because we're actually going to be moving the charge around. We're moving a charge around to see at what point does it go. So let's do this. K, Q1, we'll call it, this distance we'll call D, and this one we'll call 2 minus D, because this is 2 meters minus the distance that we have to travel to get to the point where it goes to 0, right? Like that. And this is squared, this is squared. Okay? So now, essentially, we're just solving for D. So we have our setup, and then we just do a little bit of algebra to get to the answer. So these are going to